Hi everyone, hope everybody is doing well. And in chapter 11, we're going to talk about organometallic compounds. Okay, so in the previous chapter, we had seen carbon can act as an electrophile. Okay, carbon can be an electrophile or a nucleophile, but we have seen how the carbon act as an electrophile in the previous chapter. What do you mean by that is, remember, if you start with an alcohol, for example CH3 CH2OH, and between carbon and oxygen bond is the one that's going to be broken if it is going to react with a nucleophile. Okay, so carbon is partially electropositive, oxygen partially electronegative. So carbon is an electrophile, and then the oxygen is the more electronegative atom, which is the leaving group or the more electronegative than the carbon. For example, we can show it in a common example. Carbon is an electrophile, and then the more electronegative atom, like your oxygen, that's going to be the Z. Okay, and then it can be reacted with another nucleophile. So who is going to attack what? So we had seen this nucleophile goes and attack the carbon. Always negative goes to the positive, not the positive goes to negative. More electron denser species go and attack the less electron denser species. So it's always nucleophile goes and attack the electrophile, and then the carbon halogen bond breaks, or the halogen or the oxygen. So carbon is acting as an electrophile. Same thing. I mean, we can make this protonated to make it a good leaving group, but oxygen is still electronegative compared to carbon, and then the bromide comes here and then leaves oxygen as a water molecule. Okay, so carbon is a electrophile in our previous chapter. Okay, now what if we can reverse the electron density in the on the carbon atom? We can do that. Okay, carbon is electrophile when it is attached to an electron withdrawing group. Electron withdrawing group is any atom that is more electronegative compared to carbon. What if we can change or have a different atom here that would be more electropositive compared to carbon? So then the carbon has to be electronegative, and the best way to do that is to attach a metal on the carbon, because we know metals are electropositive. Okay, so here when alkyl group is attached to a metal, metals are mostly electropositive. We know that metals undergo oxidation. They would love to form positive charges, and also depending on the electronegativity scale, we know that the metals are less electronegative compared to the non-metals. Okay, so this is less electronegative than the carbon. So now the electrochemistry between the two is reversed. So metal is electropositive, carbon will become more electronegative. Now carbon now can act as a nucleophile. Okay, now the nucleophile now can react with another electrophile. So anything that is less electron density, so it can go and attack this to form ethyl group and the electrophile, and then the metal will be lost. So carbon is a nucleophile when it is attached to a metal, because they are electronegativity different. So you can see here carbon is 2.5 and all the metals. So you know that the left side of the periodic table consists of metals, and then the right side, when you look at that zigzag line, that tells you that they are non-metals on the right side of the periodic table. So one way that you can remember the electronegativity is fluorine being the more electronegative atom, 4.0. And then for the second period, it's easy to remember. You start with lithium, and then you give number 1 electronegativity for lithium, and then you keep on adding 0.5. Lithium 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay, and hydrogen, another thing to remember is where hydrogen lies in the electronegativity scale. It's 2.1. So that one is between boron and carbon. Hydrogen is here being 2.1. And if you remember that, then you always know between carbon and hydrogen which one is more electronegative. It's carbon 2.5, hydrogen 2.1, right? And then we know the polarity would be 0, not 0.4. It's going to be non-polar, because 0 to 0.4 is non-polar when you look at the electronegativity difference, when we are looking at the polarity of bonds. Okay, and then the rest of the metals, all of these, all the metals, you can see they are going to be less than carbon. So whenever any of these metals attach to carbon, carbon can act as a nucleophile. Okay. Many metals can be used to make organometallic compounds, and these are some of the compounds: carbon, magnesium, lithium, copper, cadmium, palladium, zinc, aluminum, lead, mercury, ruthenium. They all can make a carbon metal bond, and we call them as organometallic compounds. Organomagnesium, the one written first, and the organolithium compounds are two of the most common organometallic compounds. I have worked with both of these and they work beautifully. Okay. Nomenclature. How do we name them? Name the alkyl group, then the metal. So here you have a butyl group attached to lithium. So first we name the alkyl group butyl lithium. And sometimes, just to represent that it is not branched, we would say N-butyl lithium, normal butyl lithium. N-butyl lithium is a commercial name when we buy the product from the store. Okay. And then this one is ethyl magnesium bromide, organomagnesium compound. Ethyl is this side chain, ethyl magnesium bromide. And then this one, there are two propyl groups. So two. Dipropyl cadmium, and then there are 4 ethyl groups, tetraethyl lead. So that's how we normally name organometallic compounds. Organolithium compounds, how do we make them? So this compound, 1-bromobutane. You take 1-bromobutane, readily available. You put a piece of lithium, and then in the presence of a solvent hexane, we need to have a solvent for it to mix properly, and then you can form butyl lithium in hexane. Butyl lithium, that's how you form. So earlier, now with the bromine, if the bromide is attached here, bromide is electronegative compared to carbon, and carbon is electropositive. But once the lithium take place of the bromide, lithium is going to be electropositive and carbon become electronegative. You see, by changing the atom attached to the carbon, you can change the electron density on the carbon, make it a nucleophile from an electrophile. Okay. Another one, we have chlorobenzene, and then in the presence of lithium, 2 lithium and hexane, you can form phenyllithium. So lithium is electropositive, and now this carbon here is going to be electronegative. Okay, can act as a nucleophile. Organomagnesium compounds. How do we prepare organomagnesium compounds? So you start with alkyl halide, cyclohexyl bromide, in the presence of diethyl ether. Diethyl ether is the solvent, and magnesium, a piece of metal. You mix them together and then you let it stir. So you will see the magnesium insert between the carbon and bromine bond, and you're going to create cyclohexyl magnesium bromide. Cyclohexyl magnesium bromide. Now in the organolithium compounds, you could see that the lithium attached to the carbon, but the bromide is not going to be next to lithium. It's just the butyl lithium and then the lithium bromide. But the difference in the organomagnesium compounds, the halogen, the magnesium will attach in between the carbon and the bromine. Bromide group is attached to the magnesium. It's not this group and magnesium, just like the lithium. So lithium, so we call it as cyclohexyl magnesium bromide. So diethyl ether, tetrahydrofuran, THF stands for tetrahydrofuran. That's also another ether, a cyclic ether. Diethyl ether is like this. You have a ethyl group. So this is diethyl ether, two ethyl groups. And tetrahydrofuran, THF, is a cyclic ether. Tetrahydrofuran, this one. Both of these are ether and very unreactive. So we use that as a solvent when we are making a Grignard reagent. Okay. So you can also make Grignard reagent with a vinyl bromide. Vinyl part is this part, that you have a double bonded carbon attached to a bromide, a vinyl bromide, and then when you put the magnesium gonna insert between the carbon and the bromine, so vinyl magnesium bromide. So organomagnesium compounds are also called Grignard reagents, and this is very important part of organometallic chemistry. And Grignard reagent, so in 1912, so it was Victor Grignard who found this methodology, and he won the Nobel Prize in 1912 for finding this Grignard reagent. It's very important, and today we use it, and it's going to be very helpful for many of our reactions. And in fact, we also have one experiment that involves Grignard reagent that you're supposed to do it in the lab, but we will see the virtual lab later on. So the synthesis of Grignard reagent carried out in an ether solvent, because like I said, ethers are very inert solvent. It doesn't react much. It doesn't have any protons, because this Grignard reagent, once it forms, it is very reactive, and if you have any acidic hydrogens, it can destroy the Grignard reagent, because this is very nucleophilic. If you have any water in the medium, any hydrogens, acidic hydrogens, this group can go and react with that and does not function as a Grignard reagent. It would destroy it. Okay, so the solvent provides the electron so that the magnesium can complete its octet. Another thing that the solvent helps is, now if you look just the Grignard reagent, methyl magnesium bromide. So magnesium has 4 shared electrons at the moment from the 2 bonds. But if you want to make it an octet, it needs 4 more electrons. So the ether carrying its lone pairs as a coordinating solvent can give that additional 4 lone electrons from 2 solvent molecules and have a nice coordination compound and secure the Grignard reagent that you make. Okay. Organomagnesium and organolithium compounds react as if they were carb anions. So we know carbocations. Carbocations are when the carbon carrying a positive charge. So the carb anion is when the carbon carrying a negative charge, carb anion. Carbocation is C+. Okay. So ethyl magnesium bromide react as if it were carb anion, meaning you have an ethyl group with a lone pair. When you have a lone pair, so then the carbon will become negatively charged, and then the magnesium bromide would be positive. For example, you can think it like that. So the bond between the carbon and the magnesium breaks, and the electrons given to the carbon. So then you have CH3, and you have C hydrogen, and 2 electrons. Now, if the magnesium gives its 2 electrons that were in the bond to carbon, magnesium will be positive. So Mg would be plus bromide, because it's now losing 2 electrons. Now, how do we get carbon negative charge? So you can just write this one as CH3 CH2 lone pair. Now when this happens, if you just leave it like that, it's not going to be correct, because now the carbon is carrying a formal charge. Now let's calculate the formal charge of carbon here. Remember, I mentioned you how to calculate the formal charge. That is the group number. Carbon is in group 4 minus the number of bonds and the electrons on the carbon. How many bonds are there? 3 bonds, plus the number of electrons, 2. So 3 plus 2 is 5. So 4 minus 5 is minus 1. So that's why when it's a carbon ion, carbon with 2 electrons is negatively charged. We cannot just leave it without any charge, then it would be wrong. Just like OH is minus, but water neutral, H3O is a plus. Okay, so you have to write that. What was I just saying? So this is water. When you write the water molecule, you don't put any charge, but if it is OH, now oxygen has 6 electrons with a bond. Group number for oxygen is 6 minus the 1 bond and the 6 electrons 7. That will make it oxygen -1. Oxygen -1. We do not leave oxygen with 3 lone pairs alone. And then similarly, if water carrying another additional hydrogen like that, if you calculate the formal charge, it would be +1 like that. So likewise, the carbon ion with the lone pair and the negative charge. Okay. Okay. Alright, so that's the carbon ion. So it can react if they were carb anions, meaning now they can act as a nucleophile. And then phenyllithium react as if it were a benzene carbon ion. Let's say that to be safe. Benzene carbon ion. Okay. Okay, organomagnesium and organolithium compounds will react with the proton of an acidic group because now it's a nucleophile. Proton is H+, so the nucleophile can react with the electrophile. So methyl magnesium bromide. So this is the Grignard reagent. Remember, alkyl group, magnesium and bromide. Now you should be able to identify now this is as a Grignard reagent, okay, in the presence of the water. So this can act as a carbon ion, react with the hydrogen proton of one water molecule and become methane and magnesium bromide with OH group. Now this gives you some hint. If you want to carry out a reaction in with a Grignard reagent, we want to make sure that there are no water in the vicinity. Meaning when you perform your Grignard reagent, we normally put all our glassware in the oven, maybe overnight if you do the experiment in one of the learning labs. But in the grad school, when you actually do perform Grignard reagents, we have heat guns. We have heat guns in the labs also. So you can remove all the water, even the moisture in the glassware, just to want to make sure there is no water at all anywhere. Otherwise, you can see according to this reaction, it can get destroyed if there's any water. So if you want to see how it happens, so this is your methyl group. Remember, we talk about now it can act as a nucleophile, MgBr, okay, and then the water, any water in the vicinity. So this is not even an acid, just the water. So this goes and grab this hydrogen and then become CH3 will become CH4. OH, the leaving group OH, will combine with the magnesium. Now, if you really want this to react with something else that you want, then it would not be able to do that because it's now already been destroyed. And then the making of the Grignard reagent also need to be done very carefully. So basically you have to babysit the reaction. You have to watch it clearly. You have to monitor it. You have to control the temperature. You have to add the reagent slowly. So there are many things to do. After you make it, after such effort, if there is any water and if you destroy the Grignard reagent, you will not be able to perform the reaction of your interest. Okay. So we have to do some careful monitoring of the Grignard reagent. And then again, if you start with the Grignard reagent, it can react with methanol. In methanol also, you have acidic hydrogen, this hydrogen, not this group hydrogen. So this is the acidic hydrogen. So the methyl group can react with this guy, form methane, and the rest of the methoxide group attached to magnesium bromide. Again, methyl magnesium bromide. So now it doesn't have to be methyl, it could be any other compound as an alkyl group. React with ammonia, and again this has 3 hydrogens. Nucleophile attack this group, take hydrogen, become methane, and this reagent. Same thing with methylamine, and same thing with acetylene. In acetylene, these hydrogens, they are also very acidic. So this can react and take this hydrogen and form methane and the rest of the other compound. When the Grignard reagent reacts with a proton, it forms an alkane. So like I said, this could be an ethyl group, and then it would be ethane. This also could be a benzyl group, not benzyl, a phenyl group. So it would become benzene, okay, and so on. So any of these group could be an alkyl group, and then you're going to be making an alkane at the end. Transmetallation, meaning now you can exchange the metal part. Okay, so now this is, let's say this is your ethyl magnesium chloride. Ethyl magnesium chloride, you react with another metallic compound, cadmium chloride, and you can replace magnesium by cadmium. Now that happened due to the electronegativity difference. Now magnesium electronegativity 1.2, carbon 2.5, 2.5 minus 1.2, 1.3. So between magnesium and carbon there is a electronegativity difference 1.3. Between carbon and cadmium, cadmium 1.5, carbon 2.5, electronegativity difference 1. So which one is going to be more polar bond? Is it going to be carbon magnesium or carbon cadmium? The more polar one is going to be the one that has higher electronegativity difference. An organometallic compound will undergo transmetallation or the metal exchange if a less polar carbon metal bond will be formed. So this is a more polar carbon metal bond, and then with the cadmium it is forming a less polar carbon metal bond. So if that is possible, then it would undergo transmetallation. The more polar the carbon metal bond, the more reactive the organometallic compound. So between these two, which one is more, between these two, which one is going to be more reactive? The more polar bond, which is between carbon and magnesium compared to carbon and cadmium. This is more reactive. So in the presence of the cadmium, it will form this one. But let's say you have diethyl cadmium and magnesium chloride. If you try to reverse the reaction to make the ethyl magnesium chloride and cadmium chloride, it would not happen. The reverse reaction will not take place. Okay, because this is, the difference is less electronegative compared to the more electronegative compound. More polar means more reactive. Now between carbon and lithium, carbon electronegativity 2.5, lithium 1, so the difference is 1.5. Between carbon and magnesium, carbon 2.5, magnesium 1.2, 1.3. Electronegativity is more between the carbon and lithium. The more polar the carbon metal bond, so which is more polar, carbon lithium, the more reactive the organometallic compound. Organolithium compound is more reactive than organomagnesium compound. And then we have organocuprates. Cuprates means when the alkyl groups are with copper groups. How do we make cuprates? So you can start with organolithium compound. You react with copper iodide in the presence of tetrahydrofuran, THF. So a transmetallation will take place. So that we have to start with 2 alkyl lithium. So you're going to be forming 2 of these alkyl groups will be attached to the copper. It was in the lithium before, now it goes to the copper and then lithium. We call it as organocuprate or a Gilman reagent. So this Gilman reagent also has a lot of help or has a lot used in the organometallic compounds. I believe that also has some Gilman reagent here. Yeah, it's called Gilman reagent. Organocuprates. Alkyl group of an organocuprate replaces a halogen. Now, let's say once you make a cuprate, what are the benefits that we can get from organocuprate? So it can react with an alkyl halide. Alkyl group of an organocuprate replaces a chloride bromidoiodide. Now again, copper is a metal, and then this is a carbon chain. So who is going to be more electronegative? It's the carbon going to be more electronegative. Now you have a halogen here. Alkyl group of an organocuprate. This alkyl group replaces a chloride bromidoiodide. So one of these groups goes and attack the carbon and then leaves bromine. So you're going to be forming a new carbon-carbon bond between, so let me show you. So a carbon goes and attack here and then releases bromide group. So one of the alkyl group forms a carbon bond with the butyl group. Now you have 7 carbon long chain forming a carbon-carbon bond, and then the rest. So the other group, so remember we started with 2, so the other one will end up being on the copper and then the lithium bromide plus lithium bromide. And a coupling reaction joins 2 carbon hydrogen containing groups. So again with the organocuprate, so this is not organolithium, this is a cuprate since we have copper. So one of these ethyl groups can react with this carbon and then it leaves bromide. So these ethyl groups now replaces the bromide group, giving us this new compound. Okay, it would be one of the carbons goes here and then leaves bromide. Okay, that's how it happens. And then the same thing for the other one. So this carbon attack this carbon and then leaves iodine. So we can basically add this alkyl group, or in this case it's alkene, into this carbon on the benzene. Okay, so it's a very versatile reaction. So you can add handles onto the organic compounds. And when we are doing this in a cis and trans alkenes, configuration of the double bond is retained. It doesn't change. So let's say this is a cis alkene, 2 hydrogens are on the same side. So you react with organocuprates. So bromide is the halogen that is going to be replaced by the methyl group. So it will remain as cis and then the methyl group will replace bromide. Same thing, so you start with a trans alkene and here you have bromide as your halogen, and then this will be replaced by the methyl group, trans compound. Organocuprates can be used to prepare compounds that cannot be prepared by via nucleophilic substitution reactions. If you recall from your organic 1, you know normally these groups, like when you have vinyl groups, they will not undergo nucleophilic substitution reactions. But with organocuparates, we can achieve the product that we want. The alkyl group of the alkyl halide and the organocuparates. It's talking about the alkyl group of the alkyl halide. So this is the alkyl halide, and this is the organocuparate. In the organocuparate, this is the alkyl group. So this alkyl group and this alkyl group, okay? The alkyl group of the alkyl halide and the organocuparate can be a primary group, a methyl group, aryl group, vinylic group, or allylic group. So these are examples of those. Primary could be a primary alkyl, it could be a methyl group, aryl is this group, vinylic is when the double bond is directly attached. This carbon of the double bond is directly attached to the halogen, and then the allylic would be not the carbon that is on the double bond but the one next to that is called the allylic. All of these can participate as an alkyl halide and the organocuparate in these reactions, but the alkyl group cannot be secondary or tertiary. Okay. And these organocuparates can also react with epoxides. Ethylene oxide is, in another word, epoxide. Again, this can act as a nucleophile, can go and attack one of these carbons since it's symmetrical, and then it would open up the carbon-oxygen bond. Okay, so you have one of these carbons, partially electronegative, right? And then this can go and attack this carbon and open the bond. So the copper is going to retain with one of the ethyl groups, and then the other group will attach to the CH2. So you're going to be making this compound right there. This is the ethyl group that came from the cuparate, and then you have CH2 minus from the epoxide, and then when you add a acid, epoxide grabs a proton and become alcohol. Okay. The alcohol has 2 more carbons than the alkyl group of the organocuparate.